Hello, my name is Antti Roolila. This is climate lesson number 5, calculation of greenhouse effect. The greenhouse effect is based on the absorption of infrared radiation in the atmosphere. And as we learned, the Earth radiates infrared radiation starting from 4 micrometers up to 100 micrometers. And greenhouse gases can absorb this radiation over the whole range. These calculations are very complicated and they utilize the latest knowledge of molecular physics. I have used a software application called Spectral Calculator. It can be used over the internet, but it's not free of charge. I can change the altitude of the atmosphere starting from 1 kilometer up to 600 kilometers, and I can change atmospheric composition. Spectral calculator utilizes so-called line-by-line calculation method. It means simply that a wavelength band will be divided into very, very small steps, and at each wavelength the absorption calculation shall be carried out. And this method utilizes HITRAN database. This means that the properties of the greenhouse gases are based on two things, on theoretical calculations and the measurements carried out in the laboratory conditions. This is how the opening page of Spectral Calculator is looking like. You can select Earth, upward, downward, and then you can select what is the height, what is the atmosphere. There are 6 atmospheres available: polar zone, summer, winter, mid-latitude, summer, winter, and tropical zone, and USA standard atmosphere. And here we have greenhouse gases, and using scale factor you can change the concentration, and also the temperature can be changed. You may be aware about global climate models known by name as General Circulation Models, GCM, but they utilize much simpler methods in absorption calculation than this. There are some test results where using HITRAN database and line-by-line method has been compared to the real measurement values. Here I have one source where this kind of a test has been carried out. In this graphical presentation, this acronym means the real measurements, and this acronym means the theoretical calculations. The wavelength range has been from 10 micrometers up to 20 micrometers in this graph. And on this scale, we can see the mean residual. It means practically the mean error between measurements and theoretical calculations. There are the results using the older HITRAN database 96 and the latest database 2000 at that time. Nowadays we have a HITRAN database 2008, and this red line here, it's drawn just by eye, and it means that the error is less than 1%. And in practice we can say that the calculation method using HITRAN database version and line-by-line method is very accurate indeed. Let's look at what happens to the radiation emitted by the sun and emitted by the Earth. Something happens in the atmosphere. And let's start from the shortwave radiation emitted by the sun. This is the intensity curve of the sun. And as we compare this curve to the red area here, which is the radiation received on the Earth, so we can see that there are some differences. Something happens in the atmosphere. Somebody is biting this radiation on the visible light and on the infrared light frequencies or wavelengths. The reason is, and the guilty one is, water vapor. It has absorption peaks starting somewhere 1 micrometer to 2 micrometer, and they are causing these bites on this side. Then we have ultraviolet light and shortwave visible light. There is also something going on. There is a strong absorber which is absorbing ultraviolet light, and it is ozone. And this is useful because ultraviolet light is harmful for all living organisms, plants and animals on the Earth. And as we know, the late 70s, it was discovered that the ozone layer over the polar joint is getting weaker. The reason was man-made chemical compounds which were used in cooling refrigerators and so on. Nowadays, they are banned. They cannot be manufactured anymore, and the situation is getting much better. Another reason is so-called relay scattering. This is the form of scattering caused by particles, atoms, which are smaller as the wavelength of the radiation. And this scattering is inversely proportional to the fourth power of the wavelength. That's why this phenomena is very strong on the short wavelength radiation. And this is the reason why we have blue sky, because violet and blue color is scattered more than, for example, red light. And it's also causing the yellow color of the sun. If we were in the space, the color of the sun would be white and the color of the sky is black. Let's see what happens to the radiation emitted by the Earth's surface. This medium curve is about the radiation intensity at the 15 degrees Celsius. And we can see that this radiation wavelength starts somewhere 3-4 micrometers. It continues up to 100 micrometers. Here the upper limit is 70 micrometers. And we can see here that if we are measuring this radiation in the space, this is what we receive. The other parts of radiation have been absorbed by greenhouse gases. And what are the main absorbers? Absolutely the biggest absorber is water vapor. It has a very wide range of absorbing wavelengths. And the weakest point of absorption wavelength is around 10 micrometers, where the intensity of the radiation is the highest. That's why this part in the absorption wavelength is called the window of atmosphere, because so much radiation can escape directly into space. The second strongest absorber of this infrared radiation is carbon dioxide. Its maximum peak is around 50 micrometers, and we can see that it's heavily overlapping with the water vapor. Here we can see also a peak which is pretty strong, and it is caused by ozone. Even there is so small amount of ozone, it is absorbing wavelength of 10 micrometers. And one reason for this is that the ozone concentration in the stratosphere is almost 100 times bigger than in the troposphere, and it is causing this peak around 10 micrometers. Then we have methane. It has just one absorption peak around 7-8 micrometers, and at the same wavelength also nitrous oxide is absorbing. They are overlapping on each other and overlapping with water vapor. So this is the general idea what's going on for these radiation absorbance in the atmosphere, and we are going to the details later on. What should be the attitude applied in absorption calculations? There are slightly different solutions used in different studies. I have used the altitude of 11 kilometers, which is the average altitude of troposphere. And I have found the reasons which I have listed here why to use this altitude. The first thing is that the absorption of radiation happens very quickly in the lower part of the troposphere. Up till 2 kilometers, already 95% of absorption has happened. At 11 kilometers, 98%, and absorption is completed at 120 kilometers. And in fact, the warming has been found in the troposphere, which has effect on the surface temperature. And one reason is that carbon dioxide has been considered one of the major reasons for warming, and this effect ends at the tropopause. I have calculated that the maximum relative portion of carbon dioxide effect is exactly at 11 kilometers. Thereafter, the effect declines because ozone starts to increase the total absorption, but carbon dioxide cannot absorb anymore. And the atmosphere consists of 4 layers, where temperatures vary in large limits. For example, the temperature of minus 25 degrees can be found in each layer, and it's very difficult to understand how and in which way the temperature change from upper layers could find its way on the Earth's surface. So here are my reasons why I think that the 11 kilometers is good solution to calculate absorption.